please understand that we will not be able to delve into the science of heat transfer, gas emissivity, NOx generation, and the origin and operation of traditional analytical technologies as we did in the extended seminars. We will have a time at the end of the presentation to answer as many questions as time allows, and we would be happy to host smaller groups in private sessions via internet meetings or in person if you would be interested. These fired systems are some of the earliest crude processing facilities, and they were known as vat stills. The flame was stoked underneath an iron vat to boil crude oil, and the system had a condenser on the off gas to capture whatever valuable hydrocarbons were of interest. The earliest was designed to capture kerosene. The vat still design was first used in Canada in the 1850s, and these systems were the predecessors to the modern-day combination of fired heaters and distillation columns. Water tube boiler patents can be found dating back to the 1700s. Both types of fired systems, both boilers and process fluid heaters, were very crude in design and relatively small in scale up until the 1910s and 1920s. As the demand for capacity increased in the residential, commercial, and industrial sectors, so did the size of the fired systems. This coincides with the understanding of heat transfer and the development of quantum theory and its application to fired systems. While working on a neighboring boiler's oxygen analyzers, I was able to see the first boiler installed at the old Gulf refinery in Port Arthur, Texas, which is now Valero. It was built before 1910 and was put together with no welding, but only rivets. Kind of shocked me. We have come a long way as an industry since these days in the design of fired systems. However, very few changes have occurred in the science of flue gas analysis and the use of these measurements in controls and protective systems. Today, fired heaters have taken on many forms and are designed for very specific functions. The modern-day process fluid heaters commonly used in refineries were developed in the late 1940s and 50s. The basic design elements have changed very little, though materials of construction have had some advances in the thermal efficiency. The companies that design them have an intimate understanding of the purpose of flue gas as it relates to transferring the generated heat into the process fluid, whether it's used for vaporizing, cracking, or just heating. This understanding of the impact of flue gas composition is largely lost between the heater designers and the people that are actually operating them. These folks in the field responsible for maintaining and operating the equipment are very aware of the potential hazards associated with the fired systems. Also, most fired heater manufacturers are not responsible for the controls, instrumentation, or protective systems, but rather only build a guideline of how it should be operated. This missing link between an ideal design and antiquated approach to controlling the equipment has only recently been addressed. While boiler codes such as the NFPA 85 go into a great deal of detail on how the equipment should be designed and maintained, there is very little information on how the flue gas should be instrumented, controlled, or used as part of a control system or protective system. This vacuum for a baseline of design has led the American Petroleum Institute, which is the largest collection of users, to build a recommended practice for the oil and gas-fired heaters, which was released, the latest version was released in 2008. And in the absence of a universal standard for process fluid heaters, such as the NFPA provides for boilers, several petitions were made to the API to elevate the status of their recommended practice, number 556, to a standard so it could be used as the benchmark for the design of protective systems. And I've had the good pleasure of sitting in on these 556 meetings twice a year for the last few years, and very proud of the progress they've been able to make in this area. And to give you an idea of the magnitude of relevance fired equipment has in our world, here's the breakdown of the total energy consumed in the manufacturing sector just in the USA. These statistics were gathered in 2002, which was the last time the U.S. Department of Energy delineated the data into these types of categories, which includes fired heaters and steam generation. The total consumption in 2014 was about 27 quadrillion BTUs of energy, or 27,000 trillion BTUs of energy. Assuming these percentages are so close to the 2002 values, that would equate to over 18 quadrillion BTUs of energy consumed just for fired processes in the USA. As we will cover in this presentation, even the most state-of-the-art heaters are only about 60% efficient at transferring the heat energy from the fuel source into the process fluid. That brings us to today's topic of flue gas, which is the byproduct of oxidizing fuel and air. As heat energy is a major component in most industrial processes, the most common way to obtain heat is by the burning of fuel and oxygen. Burning pure oxygen poses many risks and requires the separation of nitrogen. So the common medium for oxygen is just to use ambient air, or in some cases even preheated air. Fuel can be anything that burns, but in most industrial settings, that would be coal, fuel oil, or a mixture of hydrocarbons and hydrogen. The ideal product of this process is a mixture of water vapor, CO2, and oxygen, and it would also produce heat. CO2 and water vapor are the critical gases in the mix that actually radiate the generated heat. Nitrogen and oxygen do not absorb or emit any substantial level of heat energy, and increasing their concentration in the fuel-to-air ratio would only dilute the flue gas. Theoretical air, or the amount of air to completely oxidize the fuel with no oxygen left over, would only provide the byproducts of nitrogen, CO2, and water vapor. This is what we would call a perfect stoichiometric mix. What you should see in the field are systems running with a minimal value of excess oxygen, as is the intended operation of the system design. Unfortunately, most fired systems are operated with elevated levels of excess air. Nitrogen and oxygen dilute the water vapor and CO2, and in high levels react in and around the flame to form NOx, which is a heavy pollutant. If the air-to-fuel ratio goes fuel-rich, the byproducts would range, would also include CO2, possibly hydrogen, and if there was enough fuel present without enough oxygen, the flame could possibly go out and even be producing fuel. So if methane was the fuel in this case, on this little Scotch boiler, you would see the possibility of methane going all the way through the flue gas. The possibility of pouring these combustible gases into a chamber that is already on fire is the most common reason operators prefer to supply the very high levels of excess air which in their mind acts as a safeguard. Another consequence that's not commonly known to running a system with a fuel-rich mixture is also a loss in flame temperature, or a less temperature in the flame. Although there have been many advancements in fired heater construction and use, very little change with the instrumented systems relating to the fuel to air and the mixing. When fuel systems were first on the industrial market and sized accordingly, fuel had a very consistent air demand, as it was either a constant flow of pulverized coal, fuel oil, or natural gas. As industrial facilities grew in size, many of them learned to capture the off gases around the plant and mix it into the fuel. Unfortunately, the instrumented systems have seldom been upgraded to adapt to the continuous fluctuation in air demand. Most facilities that use gas for fuel measurements do account for a BTU content, which typically goes to the environmental governing body, but that BTU content is not used in any type of feed-forward design for a control system. So what you'll see on most typical systems in the field, on the fuel side of the fuel-to-air ratio, is only a volumetric measurement of fuel. And there's also a control valve that's typically controlling the pressure that is manipulating the amount of fuel delivered to the burners. But there's no compensation for a density change. So not all gas forms of fuel have the same type of air demand. And here's an example. So if methane was used as the primary source of fuel, you can see that 1 mole of methane requires 2 moles of oxygen. Well, again, we're not putting pure oxygen into the burner, we're putting air into the burner. So subsequently, 1 mole of methane requires about 9.5 moles of air. Well, if the system were to go propane rich, which does happen in refinery settings, propane, 1 mole of propane, requires about 5 moles of oxygen. And the result is you get a higher value for CO2 and water vapor. And 1 mole of methane would require 23.8 moles of air. So the air demand of propane is 2.5 times greater than the air demand of methane. Very few systems in the field have any type of feed-forward information for a rapidly changing fuel content. And this is where the systems rely on the feedback measurements of the flue gas analyzers. On the air side of the systems, very few fired systems actually measure the air flowing into the burner, and fewer still have the ability to modulate the airflow to keep up with a changing fuel source. Fired systems have many different types of motive forces for the air to move through the heater. There are systems that use a forced draft, that use a blower to push the air into the burners. Some use an induced draft fan that is designed to pull air through the heater. A balanced draft system would have a fan both on both sides, on the high and low side of the heater, to create a constant flow in both directions to pull air through the heater. But most refinery fired heaters are what we call natural draft, and they use the buoyancy of the heated gas inside of the flue to continuously pull air in, create a vacuum inside, which naturally allows the air to flow through. In all cases, there are some typicals. And one of those is, again, that there's no air measurement of volume of air flowing into the burner. So, like I said earlier, there's no density, no mass flow of fuel going into the burner, nor is there an airflow going into the burner. And on most systems, the mechanical controlled elements used for manipulating the airflow have to be manually adjusted. So on a natural draft system, you would have an air register at each burner, and the register would be opened or closed to a certain position to allow an airflow through. And the damper would be on the stack, and the damper would be used to create the necessary pressure inside. I've seen it many times in the field where the operators think that they should be using the damper to control the airflow, when it's the inverse, that the register should be what the final control element used to change the airflow. So whenever you change, let's say you wanted more air going into the heater and you opened up the stack damper, what you're doing is creating a lower resident time of the flue gas inside the heater. So while you are generating more flow, you get less heat transfer because the flue gas is inside of the chamber for a shorter amount of time. And if there is some automation of the air, the most common place to see that is on the damper, but very seldom do you see that on the registers. So companies that think they're having a gain by automating the dampers are sacrificing thermal efficiency by shortening the resident time of the flue gas inside. No matter the fuel or air control mechanisms, the design of the system is to operate with a minimal concentration of excess air in order to facilitate the required heat transfer. It is well understood through practice that there are efficiency gains by operating with less excess air. But what you see on the chart here is as the oxygen is decreasing, you hit a certain point in the stoichiometric mix where you can have a rapid onset of combustible gases. And if you keep on pushing that air down, eventually you could have fuel breakthrough. And again, these systems that were designed in the very early days, the thermodynamics and quantum theory, they really didn't understand that. They just understood there were efficiency gains by minimizing the excess O2. And inversely, there was a risk of minimizing it too far where you have a production of combustible gases. So each type of fuel is going to have a different level of CO2 output, as I showed you earlier with methane and propane. And here's some examples on the right side of the screen as the different levels of CO2 in the flue gas from coal all the way to natural gas. This may help you visualize the dilution of CO2 and water vapor when applying more excess air. So what you see on the bottom of the screen is the excess O2 from 1% all the way to 10%. And as you increase that excess oxygen, the partial pressure of water vapor and CO2 decrease. And whenever you impact that partial pressure, not only are you diluting the critical components for heat transfer, but you're also affecting the gas emissivity overall. And as that gas emissivity drops, the loss of heat transfer falls with it, or radiation efficiency. The net result of increasing the excess air is the requirement of more fuel input into the system to compensate for the loss in radiation efficiency. These values of radiation efficiency and you see total heat liberation. This was a customer asked us to provide them with a calculation of efficiency based on reducing the excess O2. And a lot of companies have calculators to make a crude calculation of how to formulate such a change in the system. But in all actuality, there are dozens and dozens of variables, and many people leave out the radiation efficiency. So in this example, the customer was operating a UOP-style reformer, and there was only tubes inside the radiant section, and they went out into a reactor to make methane. And they were operating the system at about 7% excess O2 and wanted to lower it as much as they possibly could. So we built a calculation to show them what the gain would be, taking it from 7% to 1%. And as you can see on the screen, the total heat required, or BTU required, to operate the heater at 7% is about 140 million BTUs an hour. And if they were able to safely lower it to 1%, that would be the result of about 20 million BTUs an hour, and at $4 per million BTUs, that was over $2 million a year in savings just from lowering the excess O2. Now, this does not take into account the thermal efficiency gains on throughput. So the rule of thumb that we've come to find is that for every 1% excess O2 you're able to reduce, you can see about a 4% increase in throughput of the process fluid. So the API wanted to build some very generic terms on where to set this magical O2 set point. At these seminars, I would ask the room, where should the O2 set point be on a process-fired heater? And we would go around the room, and you would hear 3%, 2%, 1%, 5%. And if you were talking to the operator, they might say 8%. But in all actuality, there is a way to come up with a both efficient and safe means of evaluating where that O2 set point should be for every type of fired heater. So some of the language that they use in this API 556 is that in order to determine the O2 set point, you should do a combustibles breakthrough check. So that means manually lowering the air to find a place where the combustible breakthrough occurs. And there's many variables that would impact where that's going to happen, and they include tramp air flow rate, condition of the burners, fuel gas composition, bridge wall temperatures, but it also includes wind fluctuations, wind direction, barometric pressure, and potentially operator error. So as I say, the combustible breakthrough would typically occur between 0.5 and 2.5%, but it could be outside of that range. So once you find that value where combustible breakthrough occurs, then you need to establish the O2 set point. So finding the breakthrough doesn't give you the set point. That just gives you the point where you know you're producing combustibles. Finding the set point, you should have some evaluation of the overall system to determine that if you had a process step change, a change in the load or a change in the process, you would be able to have sufficient time to correct the combustible occurrence if it were to happen. And also that in a properly designed system with fast responding diagnostics for flue gas, it is acceptable to operate them at less than 1%. So this has been very shocking to several people we've worked with. But we, Yokogawa, have over a dozen systems worldwide where a very large-scale heater is operating at less than 1%. And we have several customers who have done their own controls and have all the proper diagnostics and layers of protection to safely operate even steam methane reformers that are over 200 million BTU an hour systems. So here's an example of what that process would look like. This was a client very early on in our development of the TDL technology, and they were wanting to determine what kind of efficiency they could squeeze out of a furnace before making any modifications, before buying new burners, before coating the tubes, before they were even potentially going to replace the entire convection section, hoping to get some more throughput. So they normally operated the heater at about 4% excess O2, and as you can see from the test, as they lowered the excess O2, when they get below 2.5%, there started to be a little bit of CO generated. And whenever they hit about 1.5%, you see a very large spike in the CO production. So this proves to them that they can safely operate the heater around 2% excess O2, and they would have to evaluate the overall response time of the system to determine what type of margin they would have to put on top of that value. So understanding that oxygen and combustible type analysis can provide some value, we wanted to look back and see exactly when in history people started to understand the value of the trimming of boilers and process heaters. So in our search, we found this article from 1922 from Power Magazine, and inside of it you can see there's this great little statement about in order to tune it, the operator would have to have an ORSAT, which is a wet chemistry type of analyzer, equipped nearby the heater, and take grab samples out of the flue gas and put them through the agents, and it would give them values for CO2, oxygen, and CO. So in their 1922, they were saying that the operators would have to learn how to work the process, and it would take about 15 minutes to come up with these values to determine if they needed to manually change any of the settings on the heater or on the boiler. So fast forward almost 100 years, and today there are many common measurements used in flue gas analysis, including oxygen, and this is probably the most common measurement, and it's a great key indicator as to the performance and safety state of the fired system. Most common technologies used on fired systems are paramagnetic, zirconium oxide, and now we're seeing a lot of these tunable diode laser spectrometers used in oxygen. The paramagnetic is primarily used for emissions monitoring. These analyzers require that you pull the sample out of the furnace and remove the moisture content, and that creates a bit of a volumetric error, but that's typically okay for what why they're using them. I have seen operators on large crude heaters and refineries use the paramagnetic value for trying to trim the heater. And I was doing sort of an audit on this crude heater, and there were 13 burners, floor-fired system, and each burner had the capacity for about 20 million BTUs of energy. And we had tunable diode lasers installed inside of the radiant section. So the O2 measurement at the stack on the paramagnetic was reading about 2.3% excess O2. And I crawled up on the heater and saw that the TDL O2 value was 0.7% oxygen. So I scrambled off the heater, went and found the operator and said, "You're probably not in a safe state. Would you come take a look at the heater?" Well, we found that one of those 13 burners was fouled, and the flame was coming out 90 degrees to the burner and shooting a flame that was impinging on all of the tubes on the side of the heater. So again, the methodology for paramagnetic analyzers, it isn't typically recommended for using it for trim control. So most commonly, oxygen measurements in general are just used as a monitor or as a health check indicator for the operator. And if there's some value that's out of the permissible limit, typically there's an operator response. Sometimes oxygen analyzers are used for closed loop control. This is typically used in conjunction with a air-to-fuel ratio controller with an airflow measurement going into the burner, but not always. The most common measurement other than oxygen has been what we refer to as combustibles. The original analyzer sensors used in flue gas analysis were developed for the safety of personnel in mines, which was a giant scientific leap compared to lowering a poor canary down into their possible demise to find out if there was sufficient oxygen or any toxic gases. And what you see on the top right of the screen, this is a very elementary concept of what we would call a catalytic bead, where you have one bead that's doped with a catalyst and another bead that would be used as the reference bead. And it would be held at a temperature at which the target gas would oxidize. And the most common gas that it's trying to key in on would be CO. So in most cases, these are held at the temperature at which CO reacts and oxidizes, and this is why it's most commonly called a combustible analyzer. So the common uses for this technology are usually an indicator for an upset. They're not, you can't really diagnose which type of upset event has occurred, but it does give you an idea that there's something going wrong inside of the heater, because this type of sensor can't distinguish between CO, which would be the consequence of incomplete combustion, and hydrogen or methane, as that would typically indicate a loss of flame. Sometimes we have seen these tied into safety instrumented systems, but it's a very rare exception. There are some analyzers that have the ability to measure CO specifically, and the most common devices are infrared photometers, and the most common infrared photometer you would see would be installed on the stack of a fired process, as they have an upper temperature limit of about 300 degrees C and a maximum distance of about 30 feet. So installing one of these inside of a firebox just isn't feasible with the type of technology it is. And another is laser spectrometers. And there's different types of lasers that can be used, from distributive feedback to VCSEL to diode lasers, quantum cascade lasers, intraband cascade lasers. But all of these typically can be tuned to a CO-specific wavelength. And these technologies have only been around for a couple decades and commonly used in the last couple decades. But again, the CO-specific measurement can be used as an indicator of some type of upset condition. If you were to look at a type of fault tree analysis, you would see that there are many potential sources of the type of upset that would lead to CO being generated in the flue gas. The most common use, I've been involved with hundreds of these types of spectrometers used for CO specific, but the vast majority of them are just used as a monitor that puts in an alarm to the DCS for an operator to respond. Sometimes we have used these, tied them directly into a basic process control system as an override to fuel pressure. So again, the pressure of the fuel delivered to the burners is modulated with a control valve. And if there were some type of upset in the system and CO was generated, it's a very basic algorithm to use this as an override to that fuel pressure. And sometimes customers have even used the CO-specific measurement as part of a larger cross-limiting control to auto-tune the fired system. Another type of flue gas measurement that has become more relevant of late is methane specific. So again, the combustible analyzer is not necessarily tuned for methane. Though you see on the screen there are catalytic bead and thick thin film technologies that can be tuned to methane, just because it's called a combustible analyzer does not mean that it will pick up methane as part of the sensor response. Laser spectrometers are also becoming more prolific in this area, and the specific use of the methane measurement is to try to diagnose a loss of flame in the system. Now, if the fired system is up and running and you were to lose the flame at the burner, that doesn't necessarily mean that you would see methane at the top of the radiant section or in the convection section. The auto ignition temperature for methane is about 450 degrees C. So if raw fuel were to enter into an environment above that temperature, there would be sufficient heat energy and oxygen to continue to burn the flame. And methane-specific measurements have also been used as a startup permissive on purge cycle. So if you're not familiar with the startup procedure on a boiler or fired heater, before they light off the pilots, they typically purge it with steam. And this is to remove any potential fuel gas that might be in the system. So the methane-specific measurement, we've seen it more common now, where they use the methane value to determine that the purge cycle was effective. So getting a little bit deeper into the oxygen analyzers, again, the most common type of oxygen technology is zirconium oxide, and this sensor was developed in the 1950s and purchased by Westinghouse, but the technology applied to fired heaters really wasn't adopted in the industry probably until around the 1980s that we saw very commonly used and considered the most effective technology. And there was a lot of reasons why this technology was popular. One, it was relatively low cost. What you'll see in most, especially refineries, you'll see a distillation column with layers and layers of instruments and advanced control, and next to it is a fired heater with maybe one control loop. So very little money has been invested in these fired systems, but fortunately, these zirconium oxide analyzers came in very reasonable cost, and were also very reliable, and one reason for that was this was a solid state sensor. So what you're seeing on the screen are a few different varieties of how the sensor would be exposed to the flue gas. The sensor does have to be held at about 700 degrees C for it to operate with the most efficiency. They will be able to measure oxygen at lower values than 700 degrees C. It's just not as effective, it doesn't have a good sensor response. So the API wanted to be very clear that there are some concessions or concerns with the use of zirconium oxide for flue gas analysis. And then these two statements show one of the most critical times in measuring oxygen as part of a protective system is if you go sub-stoichiometric or fuel-rich and start generating fuel potentially or even CO. And what it says here is that if you do have hydrogen, CO, or even methane, it has a potential to mask and malfunction low the true O2 value. And that has to do with these components actually oxidizing in and around the sensor, consuming the oxygen and causing that false low value. Another aspect of zirconium oxide sensors is that they require a reference air, and that's typically used with instrument air. If the facility uses nitrogen to back up the instrument air, and the instrument air goes down and the plant switches over to nitrogen, all of your zirconium oxide analyzers would fail high. And if they're tied into a closed loop system and you have a malfunction high, there's a potential that it would actually drive up the fuel pressure to overcompensate for what looks like to be too much excess oxygen in the system. And probably the most important component is that oxygen analyzers do have, in most cases, a heated zirconium oxide probe, and that sensor is a potential ignition source. So they list some mitigation options to try to mitigate the potential hazard of that spark plug causing an explosion inside the heater. But this has been the point of much consternation, especially in the boiler world with the NFPA. And Dow Chemical learned this and made a great publication at the Ethylene Producers Conference. I guess that was about 8 years ago, where they had an ethylene furnace, a very expensive fired asset, that was turned off for maintenance, but they had a zirconium oxide analyzer in the stack, and it even had what we call a flame arrestor on it. And the flame arrestor is a sort of centered metal designed to diffuse any potential fire around the sensor. Well, the sensor was left on, so it was up cooking at 700 degrees C, and there was a flame arrestor, which was designed to be a layer of protection. Well, they had a leaking fuel valve inside of the heater, and it filled the entire flue up with fuel gas. And the investigation showed that they determined that it was the zirconium oxide sensor sparked the explosion even with a flame arrestor. So the NFPA has built some language into the NFPA 85, and the language has changed a few times in the last few years. So back in 2012, their language said that users should use flame arrestors. So we started selling, hundreds of these analyzers into the market, and almost all of them had flame arrestors on them. And it wasn't, but a few months later, we started getting a lot of phone calls. And in the document, in the NFPA 85, they did not mention that the flame arrestor would impact the T90 response time. What was a T90 response time of 5 seconds without the flame arrestor could be up to a minute or two, depending on the condition of the flame arrestor. In 2015, they revised this to say that flame arrestors may be ineffective at mitigating an explosion, and they recommend that you cut the power to the sensor in the event of an upset, which would mean that you would be basically running blind during an upset for your O2 value. But it wasn't well taken into consideration that even if you cut the power, the cell was going to be above the auto ignition temperature for the combustibles. And that period of time cannot be defined, as all of these conditions would be changing. And then depending on your fuel, you could have different levels of sulfur or other corrosive gases. And how would you test the corrosion limit of these flame arrestors? And then what is the acceptable response time if it's being used as part of a control system? So there's a lot of unanswered questions that we certainly have been trying to educate the industry about. One of the systems we have come up with was to have a system that would automatically isolate the heated sensor from the process if you did have an upset. So what you see is an oxygen probe attached to basically a closed couple bypass or slipstream where the sample is motivated via an eductor and continuously pulled out of the process and swept across the zirconia probe. And if there's any type of upset in the system, you could send a signal from the control system or a safety system that would automatically shut a pneumatic valve. So this is being implemented more and more, and now the cost of what was a relatively inexpensive oxygen sensor, now that cost has increased tremendously. So the other type of, again, commonly measured flue gas is what we call combustible. And the API wanted to make it very clear that there's a difference between CO and combustible. So in their statement, they spell out that the sensor response is calibrated to CO, but is not specific to CO. Hydrogen does have a response factor, but it isn't as strong as CO. Methane has a very small response factor for the temperature where CO is tuned. So the API wanted to put out some language on these potential concerns, and you can see here that the catalytic bead or hot wire technology, well, it's oxidizing the combustibles on the sensor. In order to do that, you have to have oxygen present. So if the heater is running substoichiometric and there's not enough oxygen present, and you have combustibles, it's saying that you actually might report a lower than actual value at low oxygen concentrations. Well, certainly this is in the unsafe direction, and manufacturers have attempted to put in some safeguards. One of the safeguards would be reference air instead of using the oxygen in the flue gas. And again, since methane cracks at a higher temperature, it requires a separate sensor tuned specifically for that constituent. Combustible analyzers also are a potential ignition source. So if you're using this device as a layer of protection, you should probably understand that the sensor is heated above the ignition point of the fuel gas in many cases. So this also would require flame arresters and potential isolation. And also, the manufacturers do publish a T90 time, but they don't tell you exactly what the step change is associated with that T90 response time. So while they would have a T90 of 20 or 30 seconds at a percent level change, it may not be indicative of a ppm level change. So the TDLS platform is an adaptation from filter photometers that were used across the stack, and these types of platforms were first applied to fired heaters on the stack for measurements such as HF, HCl, and ammonia. Dow Chemical had the idea to adapt this platform to an ethylene furnace. And there are many advantages of this type of platform, and really can't get into all of those today. But the development of the platform for ethylene furnaces was part of a Department of Energy program launched in 2007, and it's a very detailed report that goes into a lot of specifics about not only the TDL diagnostic, but other advanced diagnostics and the control algorithms used to automatically tune furnaces, fired heaters, and boilers. So in 2007, the API invited Yokogawa to give a presentation to the committee, and there was about 150 people in the room and representatives from most major companies, and they weighed the information that we presented and decided to include it in the latest revision of the 556, which was in 2008. So they wanted to spell out that the laser-based technology was not an ignition source and also did not require reference error, and no matter the step change, has a response time of under 5 seconds and can shoot over spans of over 100 feet. I think the longest we've done is about 96 feet. And also when controlling the fired heater's air-to-fuel ratio near that magical CO breakthrough point, it's recommended that you use an infrared or laser-based specific measurement. So I know we're on a timetable here and we want to get some questions in. So I'm going to briefly go over the placement consideration for these flue gas analyzers. So the most common place with traditional technology was to put the point sensor either down inside of the radiance section or up inside of the stack. And different design considerations would have to be considered, but there are different types of distribution errors associated with both techniques. If you put the analyzer in the stack, there's a potential that air would leak through the convection section and increase or elevate the O2 value over the actual value of the flue gas. And CO does burn. It's a combustible gas. If you have CO in the radiance section, it doesn't always necessarily make it to the stack, as it would be burning inside through the convection section. The approach with the tunable diode laser spectrometers is that you can put the measurement down inside of the radiance section, avoiding the problem of tramp air ingressing inside of the convection section and CO after burning. And it also gives you an average measurement over the entire span of the heater, no matter how large it may be. So the API does have some recommendations on where to put these critical measurements. And they say that you should take the measurement as near as possible to the point where combustion is complete. Now, it's not always possible, as the vast majority of the systems were designed in the 50s, 60s, and 70s, and they weren't designed to accommodate flue gas analyzers. So retrofitting is normally required. And also, to minimize the impact of this tramp air, you should avoid measurements in the stack, both for CO and O2. And for large combustion zones, at least one analyzer for every 30 feet is recommended due to non-uniformities. A wind change could actually change the compositional oxygen across the furnace from high on one side to high on another. So multiple analyzers are usually required. So the typical fired control system as it stands today, especially for refinery process heaters, you have an airflow that is set but not measured, nor is it automatically modulated. And the fuel flow is not compensated for a compositional change. And the only control loop on the system is typically the coil outlet temperature changing the fuel pressure to the burners, and there's no combustible feedback. So what the industry has seen many, many times can be captured in Murphy's Law, where if it can happen, it will. So if the fuel density increases, the consequence is a flame that is cooled. You get a fuel-rich flame. If that continues on with no check, no diagnostic, the flue gas is cooled, and that leads to a coil outlet temperature drop. If that continues to happen, the controller says, I need more fuel to increase the coil outlet temperature. And more fuel is delivered to the burners, the flue gas is cooled more, and this cycle will continue till something happens. And that something is typically a detonation of an accumulated combustible composition inside of the heater. And after detonation is deflagration. So a very simple approach to address the accumulation of combustibles inside of the flue gas. Nova Chemical wrote a great paper, again, at the Ethylene Producers Conference. And at the end of their paper, they surmised that a very gradual decrease of fuel pressure is recommended rather than a sudden stop or even cutting the fuel off to the furnace. So the system that they recommend is that 1% fuel reduction should happen every T seconds, and it only takes a couple of variables to solve this formula for every individual piece of fired equipment. But again, this simple CO override algorithm, we were able to prove 13 times in a 30-minute time span, where we were manually trying to force up the fuel pressure to lower the excess O2. And whenever the CO level hit 40 parts per million, the override automatically adjusted the fuel pressure down at the necessary interval. So I know we've covered a lot of topics today. I really appreciate your interest in the subject matter. It is very close to my heart. My best friend growing up, I would go to his house as a kid every day, and his dad had severe burns all over his body. And as a young child, I never questioned what happened. Later in life, when I was up in my teenage years, I finally asked him what caused the burns, and he said he was an operator at a refinery, and they had some instrument producing faulty signals on a fired heater. So he went out to investigate, and the heater exploded. And 80% of his body had third-degree burns and severe disability for the rest of his life, but I was able to share the rest of those years with him. And I'm very grateful for my company putting me in the position to learn the subject matter and hopefully invoke some interest in you to want to see proper protective systems applied to these critical assets of fired heaters.